I think you may need to press your. Yeah, I think it's maybe.
I can do it by hand. Oh, so what did you do here?
Oh. Then try this again.
No. Okay, it's okay. Oh, something worked. Oh, it's just the opposite of what I expected. Okay. Up is down. That's fine. Maybe I just go. Okay. So a very classic problem in computers and in the world is that you want to distribute some objects in some storage boxes. Here's an example. So you may buy a label system where it has some labels, animals, and office supplies. And then what do? Well, you put your animals, in this case, a rabbit and a kitten, into the animal box, and your staple in the office. Okay. And this is great, but this is just a standard system you bought, and now it turns out you actually live on a farm. And then what happens is that this box gets a little on the crowded side. Okay, because everywhere you have so many animals. So this was actually not a good storage system you found. You need to find something specialized for you and your special situation. So that didn't work, but let us just instead try to use randomness. Okay, so let's just use the Wheel of Fortune. So what should we do with the rabbit? Well, the Wheel of Fortune says, go to box 10, right? And what about the kitten? Try again, goes to box 4. And the stable went to, it gets exciting every time. So you can continue this way and you will distribute your things nicely. And what do I mean by nicely? It's definitely not perfect, right? There's a completely empty box here. And this one has 3 elements. I think that's a maximum. So it's sort of balanced, but it's definitely not perfectly balanced. But this was also not a specialized system unless I was cheating with the Wheel of Fortune. The real issue you have is that you have asked your parents if you could store all your things, and one day you're missing something, right? And you want to come back, and you hope you don't have to open all the boxes to find something. So you have this burning question, where did I put Wally? And you spin the Wheel of Fortune, and there he is, right? So easy. But let's look at a real world example, right? So now you have a real world example with lots of different things in lots of different boxes. And again, you want to find Wally. Where did you put him? I don't know if anybody found him yet, but that's why we have the Wheel of Fortune. Oh, A2, there he is. And for those with not so good eyes like me, you throw him up and there he is. So you only had to open one box because the Wheel of Fortune told you which box to look at. So what is this hashing thing? So we want a fully random hash function, something like this beautiful Wheel of Fortune that can tell you where to put things, but it has to be recomputable, right? So spinning is fun. We do that with both of them, and that's fine. But then what happened was we had 12 boxes. And if they just went randomly, the probability that they got to the same box was 1 in 12. So that's good. There are 18 objects. I counted them very carefully. So that's on the average, Wally should be together with 1.5 boxes. That's an expectation. Of course, expectation, the real world is integer. So we've got something else. I think he was with 3 other guys, but it's something like that. But the point is, now 10 years has passed, and we come back and we have to find things, right? And then we want to spin the wheel again because it should be recomputable. So we always find the same thing when we get to the same object. And we succeeded, but that was because I made it up. It's impossible. Right? So we'll talk more about exactly what's impossible, but basically if you wanted an independent random number for every possible object, then you'd have to store all these random numbers. And then there could be many objects like 128-bit numbers, 2 to 128 different objects. That's a giant number bigger than the number of atoms in the universe. You can't store all these numbers. So now comes the clever thing about computers. They're not beautiful little rabbits jumping around your computer, even if you think so. They actually have numbers, right? And in this case, it's just 3-digit numbers. We don't have that many objects we worry about. And then I know that 1009 is a prime number, and it's clearly bigger than any 3-digit. So instead of picking a random number for every possible objects in the universe, I just pick 2, right? And I use them in a mathematical formula. And you can see I have orange times object, rabbit, plus yellow, and then some standard math, mod 1 to 1, the prime number, and mod 12, and add 1, because I got something that could be 0, but somehow I numbered my boxes from 1 and up, so I have to add 1. Okay. And Wally can go into the same formula. So now we only have 2 random numbers. And the point is that if we pick them randomly below 1009, and we skip the possibility that this is 0, then the probability that they go the same way is 1 in 12. So why do I have to skip 0? Why is it a brilliant idea to skip 0?
Because if you don't, the key won't have an influence on the hash function, so everything will collide.
That's a super bad case. And in general, you can't just rule out bad cases, but this case is particularly simple to rule out. And the nice thing is that's why we get strictly smaller, because if it was fully random and we had 12 objects, the probability would be exactly 1 divided by 12. But by taking out this nasty case, we can actually do even better than random from the perspective of minimizing the collision probability. Okay, so now we know how to make a storage system. We just have the design here. These things were fixed, but these numbers are what characterizes the system. And now we can just plug Wally in and find out where he goes. Goes to 10. And Kitten, 218. Goes to 3. I don't know if you can calculate this fast, but but it's possible. Okay. So now we have a storage system, and it's defined. Well, we had the 1009 and 12. They're sort of fixed because that's just the dimension of the system. We're dealing with 3-digit numbers. We have 12 boxes, and then these 2 numbers are random. The vulnerability of this system is if we have this little Tasmanian, Australian devil who actually sees these 2 numbers, right? Because if somebody sees these numbers, then we have a problem, because he knows that the cow has number 422, and what happens is that he gets there, that he's trying to hide Wally, right? But he could be far more evil than that. He could have this information, right? And then he could basically create serious problems for us. So, of course, that's what we hope doesn't happen, but he saw the random choices. So just to go back again, forget this nasty devil. If you can hide your randomness, then you can actually create the system with very good expected performance. So research in randomized algorithms often use abstract, fully randomized hash functions. But they don't exist. So then you have to think about, if they don't exist, is there any way of achieving the probabilistic property that you need? And in this case here, we were just interested in low collision probability. It was not a requirement that you have something fully random for everything. You just wanted that given any 2 things, the probability that they should collide is 1 divided by the number of possibilities. That's all we need. And that we could achieve in a simple way. And that's for storing and finding objects in computer systems, for signatures. There are quite a few things you can solve with just having low collision probability, and that's easy to achieve. So now we can ask the question, what kind of probabilistic properties can we get with realistic hash functions? So low collision probability was easy, but let me look at a different property, fair min-wise hashing. So we want a hash function that has the property that for any given set of objects, each of them has the same chance of getting the smallest hash value. It's right. So you don't know, when you design your hash function, you don't know which concrete objects you're looking at, right? So you just design one that, say, works for 128-bit integers or something like that. But you wanted to have this property that no matter which of the integers in my set I was thinking about, it should have a fair chance of being smallest. Okay. And that's extremely important. That's a huge part of Google and all these kind of companies, how they find out what's similar. And why is that so important? So here are some different old, I haven't updated the slides. I'm sure much better films exist today, but these are some kind of old films. And this is Peter, Hans, and Lars, who have written their favorite films down. And now we want to see who has similar taste. So that's what you use in recommendation systems. Okay. And I've actually put the hash numbers, those random numbers, and somehow I claim they're really useful. Because who has similar taste? Those with the same smallest hash value, of course, right? So let's try it. So the smallest hash value of Peter is 7. Hans is not doing so well. He only gets down to 15. But Lars, well, he's tying with Peter. He also got a 7. So Peter and Lars have similar taste. So I just had this big list of films, but all I had to remember was one number. And yeah, I love this old figure. So why is that brilliant? Okay, so this was basically one of the driving forces in Alta Vista, one of the older search companies, and it works brilliantly. So we could have a similar example, just 2 books. Are they using a similar vocabulary? Right. So again, we just want to hash every word in the book, keep the smallest, and compare. So we have a hash function that associates hash values with every possible word. Okay, we can use string hashing. So if they have similar vocabulary, the 2 books are likely to have the same smallest hash value. Why is that? Well, mathematically speaking, if you have 2 sets A and B, then the probability they have the same smallest hash value is exactly what's called the Jaccard similarity, which is the size of the intersection divided by the size of the union. And why is that clear? It's very simple to see, because look at the union and we distribute the hash values. If it's fair, then it's a uniformly random object from the union that get the smallest hash value. So the probability that that word is an intersection, it was a uniformly randomly picked from the union, is exactly the size of intersection. And now it's sort of easy to see that the probability that the smallest hash value comes from an intersection, that event is identical to this event, because if the smallest hash value is in both sets, then it must also be an intersection. And conversely, if it's not in both sets, then one of them has a smaller hash value. Okay, so this is super simple math. And it's one of these beautiful things where mathematical insight allow you to design something that no sort of more practically minded engineer would ever come up with, unless he read the paper. Okay, so this assumes fair minwise hashing, that every element from the union has exactly the same chance of getting the smallest hash value. If we have that system, we don't just take one, maybe we take 10 of these hash functions, right? And then we compare the books looking at these smallest ones, right? So each of these, every time we look at an index of a hash function, we have this indicator variable that tells, are they same, are they similar, different, right? And then we're just doing 10 random trials. And the mean number of times that we get a match is our estimate of the Jaccard similarity. So it quickly becomes precise when you get up to a logarithmic number of things. So instead of having to store the books, you just have to store a logarithmic number of hash values. I'm pressing number 1. Unfortunately, we have to deal with bias. So the point is, if some element has a higher chance, so we have a distribution of hash function, and if some element has a higher chance of being smaller than others, then it's bias, and bias doesn't go away when you look at averages. And I'm not going to get more into this thing, but bias is a big problem. So here's just, as I say, a bad use of hash function. We'll talk a little bit more about it, but I did this experiment, and the point was with the use of hash functions, which could not guarantee this bias that everybody has same chance of being smallest. What happened was I ran, 100,000 experiments out here, and I took the mean. And you can see as I run more and more experiments, I do have a very nice convergence. So somebody watching this system will think these are great estimates. There's a tendency that people think that if many agree, it must be right. If everybody has the same bias, it doesn't help at all. And there's a beautiful convergence to the wrong value because the value is down here. So this looks super convincing. But if you don't have the original data, then you have no clue if it's right or wrong. And if you just trust it because it looks so convincing. But then if you do it the right way, I have to read in some of my papers, but then you get the convergence to the correct value, and that's guaranteed for any possible set. Okay, and there's actually some algorithms that are considered similar because they work the same in theory if you just look at abstract hash functions, but there's a huge difference in practice. And again, these things can be problematic because if you start making decisions based on bad estimates, like where's the problems in my thing, or when I charge people or whatever, you'll never know you're wrong until, well, you're just making bad decisions. So, okay, so now we're going to get more serious. But this is just to make sure we're on the same page with these kind of things. Oh, that there. Let's start from the beginning. That's much easier. Good. So this is even the official title, Hash Function Bridging the Gap from Theory to Practice. Again, this is a BARC center we have in Copenhagen. It's a really fun place to work. How you liked it? And this is now a technical talk. Okay, start with a notation, of course, but just we're using this notation you know from programming language. You just have that the set S is just a set of smaller numbers. It's also the one you use. Same formalism you use in set theory and stuff. So a hash function is just a random map from a universe of keys to some range of hash values. Abstractly, we think of these fully random hash functions where all the hash values of the different keys are independent and uniformly distributed. But that again can't be implemented because you have to store all of them, and we think of it as a large universe. Then you have this classic linear hashing that was what we talked about before, where you pick a prime number that's bigger than your universe, you pick a uniformly coefficient A, which is not allowed to be 0, but otherwise uniformly distributed. And we define this hash function, which was the same as we saw before, A times X plus B. This was orange, A was orange, B was yellow, if you like the color version. I should have kept the colors here. And you compute it like this, okay? And the beautiful property is this thing that the probability that any two keys, given keys, get the same hash function when A and B are picked at random with these restrictions is 1 divided by the range that we're hashing to. So the target of hash function research is to design simple and reliable hashing that gives the same algorithmically important probabilistic guarantees as those from fully random hashing. And yet you can implement. And this linear hashing with low collision probability is an excellent example, and indeed the thing that started the whole area. And that bridges this theory of assuming fully random hashing with the practice. And why is this so important? Well, because randomized algorithms like hash tables, they're very popular in practice because they're simple to implement. But often this thing about what hash function to use is not really well defined, and then people get into trouble. Companies, more specifically, not people. They often don't care. Right? So what's the issue here? No test will discover if you have a bad hash function. No random test. Because if your input is random, then you don't need randomness in the hash function. You can use identity. It's a perfect hash function. Okay, so no random test can ever show that you're making mistakes. But the real world is full of data that's not random. We'll see that. And then it fails. So it's first when you put it out in industry, in real application, that things fail. And you can't even find out. Because then you have a big complex system and something goes wrong. And then you try to run another test in your hash function. Oh shit, you did random. Then it doesn't work anyway. And actually, typically, the problem is reliability. So you can do 10 or 100 experiments, you still won't see the problem. What really goes wrong is that the things that should never happen, that you've calculated should happen, lessen the probability that we get hit by meteorite tomorrow or something like that happens maybe with quite high probability. And we're going to see that. And this was indeed which got me started at AT&T, because we had systems that shouldn't fail, and it was the hash function that was the devil. So application hash function was the one we saw. So I use this curly arrow to sort of indicate where a key hash to. It's ahead of a list of elements that have the same hash value. So in this case, I've used the storage system here where I've now not stored a rabbit and a Wally, and I want to see if X is stored in the system, and I just go to the right list because that's a hash value that tells me where to go and see if it's there. It's not there, but I can add it and I can take it away. It's a very simple system. But as opposed to having to go through all the elements, I'm just looking at this restricted number, which is only in expectation a constant. Right. So with a couple collision probabilities 1 and R, the expected chain length for where X goes is N divided by R. And that holds no matter whether I use this nice fully random hashing, which is an abstraction, or I just use linear hashing. Then we have linear probing, which is often much better in practice. So here, what you do is you hash into it's called open addressing. You're hashing into an array, so all your elements are stored in an array. But this means that somebody else may have taken your place, right? Before we had a list of elements that were in the same place. So that's always a problem with hash table. How do you resolve these collisions? Here we do something very simple. If the place is taken, we just go to the next. If that's taken, you go to the next until you find a free spot. When you find a free spot, if everybody uses this system, well, then you can just put it there. But if you found a free spot before finding your element, you know it's not in the list. So the property we maintain for this thing, the invariant we maintain, is that every element that between the place that an element hashed to and the place where it resides has to be filled with other elements. So as soon as we meet an empty location, we know that the search is over. Okay. So this fully random hashing goes back to the 50s, as far as I recall it. They used it even with these hole cards when they couldn't even write assembler, but had to actually push holes to explain to the computer what to do, directly bit coding things. But Knud's proved that if the fill is, I wrote this a stupid way, if your table is 1 minus epsilon full, then the search length is 1 plus 1 divided by epsilon squared divided by 2. Remember that number. No, I mean, so basically you only use linear probing if your tables are roughly half full. That's what you should think about. So then this is 2.5, right? So 1 divided by a half squared, that's 4, plus 1, 5, divided by 2, is 2.5. Why am I mentioning that? Because, I mean, a lot of theory just likes using O notation, and that doesn't tell that much about what's going to work in this kind of practice when you're down to things that really need high speed, because this is in a loop of so much data analysis, and you actually care about the constants, right? And this scheme is wonderful in practice compared with chaining. And why is that? Because with chaining, you have to follow pointers, and that's very expensive. That's actually the biggest cost is indirect addressing. I always think of a good old record player, right? When first you have found the song, you just play very nicely, but finding the right place to start is really difficult, right? So in the same way here, it's almost free. The expensive part is to get to this point, but then reading this is very efficient. Now, of course, we don't use disk as much anymore, but still you have all this pre-fetching, cache lines and stuff like that. So you get all this for free. So the dominant 80 to 90% of the cost is just getting to here. The rest is free. Okay, as opposed to chaining where you have to follow pointers. So this thing completely fails, and that was actually what failed at AT&T with linear hashing. It works with a degree 5 polynomial with some O notation, but we can make it work even better. Then we have other things, the sketching I mentioned before with the Jaccard similarity. That's another example of hashing, where we need this thing that there's no bias. And the way people address these things, so the same guys who introduced the idea of linear hashing having low collision probability, they said, well, if you need more randomness, we just go for k independence. So the two independence, which we really saw before, is just that any two keys get independent hash values. But k-independence says, give me any k keys, then their hash values, I have to decide which keys it is. But then when I pick my hash function, then it assigns them independent hash values. And we implement that using a degree k-1 polynomial, because indeed we then have these k random coefficients. And the beauty of this thing is just no matter which k keys I look at, they get independent values, even though it was only these k random values that were independent. That's a beautiful thing, but it's not so efficient, right? So evaluating these polynomials is expensive. Getting above linear hashing are very fast implementations, but when you get above that, it gets difficult. So people had studied this thing for a long time, right? And for a different application, you can ask, I mean, this is a beautiful paradigm. For any given application, you can ask, how much independence do I need? And so if I need 10 independence, I go to the shop and say, give me a 10 independent hash function. And the fine thing is, if somebody else finds a new, faster way of implementing 10 independent hash functions, then I win, right? So crypto is now developing these kind of hash functions which don't do the AX plus B mod P, but works over some even fields and stuff like that. And as long as they can guarantee me they have something 10 independent, I can use it. So I can just plug and play. So we know, for example, that minwise independence requires log 1 over epsilon independence. So yeah, so this minwise, if you want the bias to be epsilon, if you want that to be little over 1, then you actually need super constant independence. That's tight. That's a lower bound as well that I did with Mihai some years back. So that has been the ruling measure for many years, but the question is if that's right. So we'll look at some different kinds of hash functions. So before we had this polynomial, the polynomial was extremely tight in the sense that you just wanted k independence and you only had k random coefficients. But to evaluate the polynomial, you had to read all these k random numbers every time. We're going to use tabulation, right? That goes back to the French Revolution, this whole idea that if you think things are difficult to compute, maybe we can use some tables to pre-compute some stuff. So this is extremely classic, many hundred years. So we use a key as divided into characters. So a 32-bit key could be 4 8-bit characters. And we will have a truly random hash table that maps characters to b-bit strings. So as long as the alphabet is not too large, like 8-bit characters, only 256 values, then I can store a fully random table. And now the hash value is computed as the hash of each character, right? So for each coordinate I have a hash function hi, a table, and I can just look up the hash value. And then I do XOR. So that's just bitwise XOR. Computers love it. And any kind of programming language that cares about efficiently support it with delight, because it's the easiest circuit you can possibly make. And again, if you just use 8-bit characters, then things fit in cache. And it's easy to implement. Here's the code. If you're used to C, you like this stuff. If you don't, you think it looks awful. But whatever it is, it's not a lot of code. If you want to do X plus B mod P, it's by comparison a nightmare. Because you have this problem, you need to deal with a prime number that's bigger than your universe. So it has to be a, say, 130-bit prime number or something like that. And you don't have direct support for that. And you have to do a mod function. And normally you don't have good support for that either. And then you have to code everything yourself. And you end up with pages instead of lines. And so this is actually the fastest known 3-independent hash function. So it's faster than a degree 2 polynomial. So it's sort of in the speed of just 2 normal multiplications in my experience. It's not 4-independent. So by the previous measure, it's a terrible hash function. Well, terrible is strong words, but we talk about things that required high independence, like linear probing, which is one of my favorite targets or favorite things to implement. It's not 4-independent. And why is that? Well, we just look at 2-character keys, where we in each position have 2 characters, and we look at the 4 combinatorial combinations. Right. Here are the 4 keys. And we see that in each position, each character appears exactly twice. So when we do the big XOR of the hash values of those 4 different keys, then everything appears exactly twice. And when we do bitwise XOR, we just get a 0. You can also say that if I knew the hash value of 3 of them, I would know the last one was just the XOR of the 3 first ones. So that's actually no matter what simple tabulation hash function I use, I just know the hash value. I just need to know these 3 guys, then I know the hash value of the 4 guy. But it totally sucks from a crypto perspective. But again, I believe this thing will always be super fast. So if you just try, I'm again putting on the business angle on it. So before we talked about that, well, linearly scanning will always be fast. Well, one reason is that all benchmarks use it, so you better be good at supporting it no matter what with the prefetching and stuff. Here it's a different issue. This uses cache. You can't imagine any meaningful computation that doesn't involve some memory somewhere. Right? I mean, it doesn't make sense to just multiply 2 with itself a lot of times, right? So if something has to be meaningful, it has to involve the fastest type of memory. So it doesn't make any sense to have an arithmetic processor that's faster than your cache. So this will always be fast. And so then you can ask, well, this thing about how much independence was needed, it turns out that the simple tabulation works perfectly for all these things, even though it's only 3 independent. Okay. And so it's a completely different type of scheme, right? Because we have with the polynomials, we had very small space, but we had, which just some coefficient, but we had to read them all the time. This time here, we have 4 tables. We don't want to read them, and we don't have to. We just pick out one location from each table, and we XOR the result. So it's a very different, so there's much more randomness in the system, and it works. So Knud's recommended simple tabulation, but only said it's 3 independent. So we have to prove that for any possible input, these dependencies are not harmful. So lots of dependencies. I can design these things with lots of dependence everywhere. I have to show it's not a problem. And to some of you, this is just a standard formula, but I just want to illustrate. How much time do I have? Okay.
20.
Okay, fine. We'll just continue then. So these are the classic Chernoff bounds from textbooks. So you can ask, if you throw balls into bins, how many balls land in a bin, right? And you can say, well, we have some expected number of balls that lands in the bin, and we can ask, what's the probability we get 1 plus delta times bigger? And this is an auxiliary formula, but this is some kind of constant. And the essential point is just that the probability of getting further out into the tail falls exponentially. That's the sort of essence of what's written here. And if it had been perfect randomness, then the red stuff would not exist. But with simple tabulation, what we have is that the probability decays exponentially, but at a slower rate. So it's not quite divided by mu, it's divided by mu, something less than mu, but a constant factor slower than it should. And there's this nasty thing here, but if I throw in balls into M bins, and M is large because it's a big storage system, so it's 1 million or something like that, then M is 1 million, M for million, and then I can write to minus gamma, so 1 over 1 million squared or cubed or something like that. There's something under the carpet, but we get the same nature as what we're interested in, namely this exponential decay in the tail, in the probabilities. And I will show a simple case of this thing here, but one of the really driving forces. So I want to throw n keys into, say, into the 1.1 bins. So not n, not times some constant, but n to 1.1 bins. And I claim that all bins only get a constant number of keys with high probability. And this is interesting because if you use a degree k polynomial where k is a constant, this is not the case. Right? If you use Chebyshev, then you have sort of like, yeah, it just doesn't help you much. You would get a polynomial number of elements in each bin, or that you would risk that. So here comes the essential claim. If I look at a set T of keys, then it will always contain a subset with log of T keys that hash independently when I use simple tabulation. And why is that true? We have some set of keys and we look at a position in which they differ. I mean, if we have a set of keys, they must differ somewhere. I just take an arbitrary position in which they differ. Okay. And then in that particular position, I look at the least common character, right? So I have a bunch of keys. I look at one of the positions and then look at the different characters. So maybe the first one has an A, the second has a B, the third one has an A. Oh, so now A became more common, B is less common. And I look down, maybe B is not even used again. I don't know. But so I take the least common character in that position. And then I pick some key X, which has that character in that position. And then I take my set and remove all other keys that have that character in that position. Okay, so this is, again, an inductive proof. So now the point is that the hash of X is independent of the hash of all the other elements, because when we composed our hash function, we took the hash of each character in each position, and now X is the only key that uses A in position I. All other keys will not have that character. So the hash of X is the only one that depends on HI of A. Nobody else depends on it. So it's independent. And then I just apply this recursively. So I use X, which was the only one that used A in position I, and then I combine it with the recursive definition of the rest. And that's it, right? Because I picked the least common position. This means that the number of keys I removed was at most half, right? So I pulled out a key, reduced the set by a factor, reducing the set by most a factor 2, and I keep going as long as there's something left. So in that way, I identify a subset U, which has a logarithmic number of keys that are guaranteed to hash independently with any simple tabulation hash function. So that was claim 1. Now comes some simple counting. The probability that there exists a set U of keys from my set that hash independently and land in the same bin is the number of keys to the size U divided by the number of bins to U minus 1. Okay. So the proof is very simple. The number of different sets I could be thinking of, I just want to use a union bound. So the number of different sets I could be considering is just n to the U. Now I need two properties in order to lose, right? They need to both hash independently because otherwise I don't care. And then they need to hash to the same bin. But if they hash independently, so if a condition on that can only increase my probability, then the probability that they land the same place, I place 1, and the rest have to go to the same place, U minus 1 of those. That's 1 divided by m to U minus 1. Okay, so now we just union bound over all these sets, and we conclude the probabilities n to U divided by m to U minus 1. So now we have the two claims, and now the lemma is easy to prove. We have this set which is size bigger than n to 1 plus epsilon, and we pick U to be 5 divided by epsilon. Then the probability that there exists a set of 2 to the U key, so I'm sort of going the other way around, right? I had the log here, but now go the other way around. The probability that exists a set with 2 to the U keys has it to the same bin by claim 1 is, now look at this set U that had a logarithmic number of that keys. So that's a probability that exists a set U of U keys that hash independently and to the same bin. And then we had the bound we used here, and we end up with 1 divided by m to the 4. Okay, so it's just a very simple calculation. But so the point was, in this construction was that we said, so when we use independent paradigm, we say, give me any set of k things, then they hash independently. But k is a constant. That's no good. Instead, I say, give me an arbitrary set that hash independently. And if that set is very large, then I can also find a moderately large subset, all of which hash independently. Could be a logarithmic size. So again, this is why we have a lot of independence, but in a different way than in the k-independence paradigm. And it also works for something like Cocoa hashing. If you've seen it, it's this beautiful scheme where you just, instead of having linear probing, we hashed into some array, and then we had to look for things. Here we hash into 2 arrays, but if X is not there in one of these 2 locations, we conclude it doesn't work. And it turns out that works, normally works with probability 1 minus 1 over n. Here's 1 over cube root n. Weird number, but that's exactly the truth. We have both upper and lower bounds. But this is a much more complicated thing to deal with, which is why I don't want to get into it. So again, we also try to implement things. These are old experiments, but the race is still on. But we have these different hashing schemes. There's this very efficient hashing scheme if you just want low collision probability, which instead of doing this mod and stuff I talked about, you do something that's extremely efficient in the programming language C. You just take A and then multiply with X and shift out whatever bits you don't care about. And here we use, to prove that this works, it's kind of a cool proof, but we use that any odd number is relatively prime to any power of 2. So when you do this A times X, you implicitly do a mod 2 to some power, and it turns out to work. And that, of course, is unbeatable in speed. 32-bit integers. Today, the table may be with 64 and 128. But that's super fast. But if we start using prime numbers and stuff like that, then we end up with something much slower. That was with a 4-degree 4 polynomial. And simple tabulation is sort of moderately fast. So I'm just saying you're sort of in the fast range of schemes. These schemes here corresponds to using a single multiplication, and we are almost beating that on this computer. This is actually a fun table to look at if you like numbers, but the basic point is just that it's at least reasonably fast. But here comes the interesting thing with linear probing. So running this experiment with linear probing with different hash functions. So these 2 lines, that's this universal multiplier shift and 2 independent. So these are the schemes that we don't know work. And they really don't work. And so what's going on here? Here I've made 100 experiments with different, so for each experiment, I picked a new random hash function from the family of hash functions that I was considering. Okay. And then I took how long time it took and I sorted them. So these are the ones that took the longest time. These are the ones who took the shortest time. And then I ran it with linear probing. And what we see is that if you use the sort of cheat hash functions, then they work great in the beginning. They're super fast. And they run really, really great. But then there's sort of like a 10% chance that things went really bad. And this was exactly what I saw at AT&T. So it was actually a coincidence I saw one of the bad cases, because often when you want to test things, you just run a couple of tests. And then this outlier happened, and I thought, this should not happen. The probability of that should be almost nothing. And yet I saw it, and I tried again, and wow, it went bad again, right? So it happened quite regularly. And this is really nasty, because this is actually what happens is the probability that things take X times longer than it should is 1 divided by X. So most of the time, there's no problem. But this means the expected time is actually logarithmic. But in fact, they perform extremely well most of the time. Actually, so this is just trying the most obvious experiment, running a hash table using keys, which is just the numbers from 0 to 100, to 10,000 or whatever it is, but just consecutive numbers. And I saw this behavior. Then these tables are shifted. Here I have simple tabulation. Here's something I don't want to explain, but I don't know how to eliminate it from the plot. And here you have the degree 5 polynomial. And both of them, what we see is that they're almost vertical, which means there was no deviation in the time. Okay, so it's completely reliable. This is a degree 5 polynomial, and you can actually see both this and this. They have a little bit of a tilt in the top. It means it wasn't completely the same numbers, but almost the same. But simple tabulation is just straight as an arrow. Okay. Then you see some shifts here, and this is basically because this is a degree 5 polynomial. This is actually a timed experiment, and the hash function with the degree 5 polynomial is much worse. If you look at it alone, it should have been maybe 4 or 5 times worse. The reason why it's not is because a significant part of the cost is the first indirect addressing. So things are shifted by the cost of the hash function, but then there's also the cost of the indirect hash function, indirect addressing, which is basically down here. So indirect addressing is around here. Then you add the hash function cost, that's this much. And you can say, comparing that with this one out here, it's actually 3 or 4 times worse. So things make sense. Okay, and it's really a very big, this is kind of shocking because again, this thing up here should never have happened. So multiplicative hashing is used in practice, but turns out to be very unreliable under this. For AT&T, it matters with these denial of service attacks because they just use consecutive port numbers, and basically linear probing with linear hash function fails with any arithmetic sequence. So this happens in practice. Good performance, even better than it should be 95% of the time, but 5% of the time things go really bad. And again, this is something that's very hard to detect from practitioners. You have a complex system, you run some tests, that's not enough to find this kind of unreliable behavior. It's easy to find something that goes wrong all the time, but this is not so easy to repeat. So it had actually gotten a reputation of being bad. We realized it went bad. And then we had a second system we had to switch to, but then you had two different code bases you had to maintain. It's not a very good thing. So we proved that actually it does work if you use a good hash function. So that simple tabulation is a powerful chaining, cuckoo hashing, and minwise hashing. So it works for almost everything. Then we came up with something far more powerful, but I don't know if I have time to talk about it. Do I have 5 minutes left? No, okay, I will not get offended if people leave at this point. I will pretend, I would just take one sip of coffee, look away, and do a minwise hash to see if somebody left. Okay, so this is something I did with some of my students and postdocs before she turned up. So we're going to have a more algebraic view of things. So if I have a set of key, a zero set is one where in every position, every character appears an even number of times. So this is an example. So here we have a set of 4 keys. And if no matter which position, we have 2 different positions, and in each position, each of these characters appear an even number of times. And we just talk about this in a more general way. Okay. And if you have such a set, then again, by definition of the XOR, if you have a 0 set of keys, then when you do the XOR of the hash values, you always get a 0. Because you're just XORing bit string, each bit string XORed an even number of times. So this is sort of the natural generalization of the problem we had, proving that simple tabulation is not for independent. I will say that a key set is linearly independent if it does not contain a 0 set. So if we don't have such a set, then I call it linear independent. And I have this cute lemma that says that a key set is linearly independent if and only if simple tabulation is fully random. So if I'm so lucky that somebody gives me a key set without a zero set as a subset, then simple tabulation is the perfect hash key. Okay, so there's really only one bad case. That's these zero sets, where you have either have complete dependence or no dependence. So that's a very nice situation. Okay. So, I mean, somehow this linear dependence, these zero sets, why would they appear? Right? You have to. How can you be so unlucky that for every position you have C positions? And for every character, they appear an even number of times. It's sort of shouldn't really be something that happened normally. But of course, if somebody construct a set like our 4 keys, which just had these 2 characters, then it could happen. So the idea will now be to try to take a randomizing function that takes a key and randomize it, such that if you look at the randomized keys, then with high probability they're independent. They're linearly independent. Because then I know that if I, after that, apply a simple tabulation hash function, then I get something that's completely random. Okay. So this is just the idea. We are saying that if we have a linear dependent in key set, then hashing works beautifully. Right? But we don't have random keys. I mean, we know any hash function works great on random keys. Identity works great. So that's cheating, right? But I'm still thinking there's some hope here. So that's what we're going to do. We're going to define a randomizer on keys so that I will have this C lookup. So when we compute the hash simple tabulation hash function on a key with C characters, we paid C lookups. Now I'm going to add D lookups. So I'm going to do C plus D lookups. And so that the probability that it is linearly independent is this big. And let me just talk about these different numbers. So they're not random. Well, 7 is not perfect, but everything else is perfect. Okay, so basically, in order to get anything fully random, I need to have some random tables that is at least as big as the things that want full randomness. You can't get full randomness on a set of a size 1,000 if you just use 10 random numbers. That's impossible, right? So I require that my alphabet is at least twice as big as the number of keys, but it's still only a factor 2. I'm kind of cheating a bit because I also have C character tables, but it's still within the same order of the set I want randomness on. So X is bigger than sigma. Okay, so you can say this 3 swallows 3 of those here, but I still have D minus 2. And now you can see if sigma is just 256 or maybe even 16-bit numbers, then this thing drops very quickly as I increase D. Okay, so I can I don't need many derived characters to get a very low probability that things went wrong, right? So it's pretty high probability. When I run my first experiment, just randomizing a key, I do get something that's linearly independent. And then the rest will be indistinguishable from full randomness because it is full randomness. And this term is just ridiculously low, but it is there somehow. 2 to the minus sigma, 2 to the minus 256. You don't have to worry about that. I should say there was some previous work which had this kind of time bound. And in theory that works, but in practice, this thing tends to be bigger than 1, and then it's not very useful. Then you get an error probability that's bigger than 1. You can't really use that for anything. And why am I saying this? Well, we have to be, in this context, we have to be a little bit careful when we use theory, because normally we say the problem size is very big, n. And then you can use that asymptotically. But now I want some tables that are small enough to fit in cache. Well, then we're not talking about gigantic numbers. And that's why I think it's actually useful to have a time bound like this. And the 3 is necessary. That's a number of matching you can have on 4 elements. So this is tight. And the code of this thing is not bad. It's basically just running. This is to compute the whole hash function, including the derived keys. So basically have this like simple tabulation. Then you do a kind of trick. You use the key and you put it into the hash function as well. And then you actually kind of use your hash function that you're generating also to use as input to your hash function. Because somehow I want to compute both the simple tabulation and the derived keys on the fly at the same time without paying anything. I'm very greedy, but it works. And then it turns out that this tornado hashing has a kind of local uniformity, which means we actually don't need the tables to be that big. Typically, they only have to be logarithmic. So, for example, we get linear probing with exactly Knud's time bound on the expected search length as long as my alphabet is bigger than log the number of keys divided by epsilon squared. And this local uniformity is good to think about it in connection with this linear probing, because so the problem in linear probing is you have these runs of consecutive elements in your table. And it's very complicated what goes on there. And I don't want to analyze it, but my good friend Knud did many years back. Well, good friend is maybe strong, but he did it many years back and he did very good research. Okay, so he has analyzed what goes on. And I'm saying, well, if I can guarantee that intervals which are more than of logarithmic size have locally have full randomness, then all this complicated stuff is exactly the same as what Knud did. So I don't even have to analyze it again. I can just use Knud's theorem as a black box because it's all local. And the same if I want to do different hashing schemes, if I want to get S samples, then even if I'm dealing with we're talking about streaming context where you're dealing with trillions of things coming by, I only have to have randomness, which is 10 times the number of samples I need, and then times log of X rather than times X. So I'm just saying you have a kind of local uniformity that's much stronger than what you expect. And that's also what sort of suggests that this thing could be very relevant for crypto and other things, because from any kind of local perspective, this looks completely like fully random hashing. Mm-hmm. So, concluding remarks, this tabulation hashing uses a completely different strategy than the polynomials. The polynomials had these random coefficients, but you had to read all of them to evaluate anything. And you actually sometimes needed quite high degree polynomials. Here instead, we have these tables that are fairly large, but we only look at a few number of entries every time we come with a given key. And we can even use the same system, bootstrap the system in tornado hashing, where we use it both to randomize the next keys and to generate the hash function. Yeah. So again, much more space and few lookups. So with the tornado hashing, we're kind of squeezing the maximum randomness out of our lookups to get full randomness on a given set with high probability. And so the open problem is really just to prove this works. So I should say there's one thing that's bad here. The implementation is easy and works quite efficient. When we submitted this paper to Fox, one of the referees had implemented it to check how efficient it is. And that doesn't normally happen with Fox, that they implement your code. The analysis is a bitch. I mean, it can get very complicated, but I mean, we have proven that it works for Johnson-Linden-Strauss, so for dimensionality reduction. We have proved that it works for similarity estimation, linear probing, all kinds of things. But you kind of have to start from scratch with the analysis. But the good thing is you take things that nobody knew how to implement. Nobody knew how to do sparse Johnson-Linden-Strauss with their realistic hash function before. And now we know. And for example, feature hashing would be an obvious candidate for something to work. But I think for most applications, I know I've convinced many people to just use this tornado for anything where they need something random, because I don't really know anything where it doesn't work. But it's not too easy to prove. So that's it.